All right, we should be live. Howdy, howdy, everybody. It's a little chilly. Yeah, I get paid by the government to debate flat earthers. Oh, if only that were true. If only that were true. Someday community gift. All right, somebody... Okay, we're gonna figure this out. Hold on. We're gonna figure out the community gift. Okay, there's a gift gallery. No. Live incentive program? No. Live events? No. No, I argue against flat earthers. Fan club. Contributors. No. Poll and gift vote? Oh, wait, you don't think the Earth is flat? Yeah, of course I don't think the Earth is flat. Don't be silly. Live goal, maybe? Is that the community? Is that the community thing? The community gift? Edit. No, that's not the community gift. I don't know. Okay, you have to set up before you go live. Oh, okay. Well, not today then. Hello, everybody. Welcome, welcome. It is a tidbit chilly. TikTok studio. Okay, so Holy Gore, you know that I'm using my computer, right? Let's see, maybe I can, oh, but I might be able to do it from my phone. We'll get started on questions. It's saying something went wrong. Of course something went wrong. We'll try one more thing and then we'll just get to answering questions. It's chilly in my home. Posts live. Okay, now if I scroll down to tools and resources, community gift. Oh. I found it. Now how do I select it? How do I make it go? Confirm. Hold on. Sorry, y'all. I'm just trying to get this right. There we go. Nice. Okay, we set it up. We did it. We did it, y'all. Thank you for the help, Oligor. Much appreciated. The community gift exists. All right, we did it. Okay, let's answer some questions. All right. Thoughts on clouds? Generally a fan of them. You know, usually, oh wait, why aren't I seeing comments from YouTube? Oh, there we go. Okay, now I should see comments from YouTube. Sorry I missed them. If I missed them, my bad. And then we should also be seeing comments from Twitch. Okay, good. Sorry. Can you explain the Hadron Collider? So it's a Hadron Collider, not Hydron. The Hadron Collider is, you know those toys that you had as a kid where you would have like a marble and it would like accelerate the marble in a circle? The Hadron Collider is like that, but with particles, like, you know, the subatomic particles, and it just smashes them together. And in the same way that, like, if you're really, really diligent and you smash together two clocks, you could eventually figure out what clocks are made out of. It's the same thing with the particle accelerators. Did you study soil mechanics, or is soil mechanics part of being a physicist? No, I don't think so. But maybe there are some physicists who do, but I've never met them. Could you explain what your paper about a breathing universe was about? Too hard for my brain. Yeah. So the paper was, it was essentially a thought experiment. It was a proof of concept, and I'll pull up the paper for those who are interested, so then you can follow along with what I'm talking about. I love that all of my papers are accessible from my website. It makes it so much easier to see these things. Where is it? Here it is. So the paper is here. I can just explain a little bit. So here's the paper. If anybody wants to pull it up, it's freely available online. It's basically a thought experiment. The idea is, okay, so is it possible, without using anything particularly exotic as far as, you know, as far as like the matter content is, or as far as like the laws of gravity are, is it possible that you could have a universe that is exactly cyclical, meaning that over the course of a cycle, and it has to expand and then recollapse? Oh, somebody's spamming on YouTube. Mods, please. I want to say on vertical or something. But anyway, the point is it possible that you can make a, sorry, I lost my train of thought. The idea behind this paper is a thought experiment, meaning keep standard general relativity. This is the model that governs the space-time itself and how it interacts with matter. And then add minimal quantum stuff to see if you can make it expand and then recontract in an exactly cyclic way, or cyclic way. And the answer is yes, you can. That's why the paper is called A Breathing Universe is Consistent, the breathing universe being the expansion and recontraction. And the consistency check being merely that there is a kind of matter that you can have that's not fine-tuned that gets you the perfectly cyclic universe. Now, and to be clear, this is a universe where there's a finite amount of time, because it repeats itself. Time is a circle in this model, as well as space being compact. But the important point is that, A, this is not representative of our universe at all. It's not representative at all of our universe. It has nothing to do with our universe. It's not observationally consistent with our universe. This is a thought experiment. This is a way to see, is this something that can even be possible with any kind of consistency within our known laws of physics? B, the model uses something uses an exotic kind of particle, which we don't know if it show up in a quantum field theory, called a dimension zero conformal scalar. But the idea behind the paper is a thought experiment, just to see if you can get global consistency through general relativity and quantum field theory without introducing any exotic physics. And the answer is yes, you can. So that's what the paper's about. But I'll go back to answering questions now. Why have physicists narrowed down which vacua Calabi-Yau manifolds correspond? Why haven't they? Oh, because there's like 10 to the 500 of them. So not real? Well, yeah, I never made the claim in the paper. I never made the claim that this corresponds to the universe. This is a thought experiment. How is it expanding without a central region? So the breathing model, so the real universe is, and perhaps the breathing model, these are spacetimes that don't have an edge. And so there isn't a center. There's not a center. If there's not an edge, then there certainly can't be a center. So the expansion is something that happens everywhere, not that something that happens at the edges, if that makes sense. From Sal the Handyman with the $5. Why is it doing this again? Literally just a minute ago, the text was text had a black background. Okay, well, is there currently a definition of time that spans across all branches of physics, classical, quantum, general relativity, and special relativity? Well, okay, yes. I guess you could just say that time is the dimension of space-time, that of which there's one rather than three. Three-body problem solution. The three-body problem has, like, we've known a solution, like a general solution to the three-body problem since the early 1900s. Unfortunately, the solution that we have converges really, really slowly. So, like, it's not a very efficient solution, but it is a solution. Or it is the solution, rather. Why does light have a speed limit when it has no mass? It has a speed limit because it has no mass. Radioactive decay rates are not constant, they are affected by neutrinos. Radioactive decay rates are, by definition, the decay rates in the ground state. Once you add neutrinos into the mix, you are exciting the ground state. And so, of course, it's going to have a different decay rate. But the point is the radioactive decay rates are like constant of nature because they're defined as corresponding to the ground state. Did you say it was inconsistent or consistent with what we know? So the idea behind the Breathing Universe paper is that its goal was to show a consistency in cyclic models, meaning that it is possible within general relativity and standard quantum field theory to have a cyclic model. Now, the model that I produced was very much a toy model. It doesn't correspond to the observations that we have in the real world. This is a consistency check, not a matching check with like observational data. Have you heard of the dark photon? I have, and I've actually made a video on it. It's a really interesting idea, or a really interesting proposal for what dark matter could be. If space is expanding and space and time are a connected structure, then is time expanding? And if it does, no, time is not expanding, just space. So the three-body problem is not a problem, no. In fact, like, astrophysicists on the regular solve like million-body problems. Can you explain what the dark photon is? Yeah, so the idea is that there could be like a different kind of matter, we would call it like a dark sector, where there are, like, think of it like kind of like a mirror, like mirror matter, meaning that like that matter can't interact with our stuff and our stuff can't interact with their stuff, but they have their own, like there are laws of physics that would govern that stuff. They would still obey gravity, but like they would have their own interactions. And the dark photon is one such possible thing that you could have in a dark sector. And there are certain ways that you can arrange those interactions in the dark sector that would make the dark photon have mass. Can the Hadron Collider be used to predict earthquakes? Is the magnetic field of the collider large enough to penetrate the Earth? Is there a specific particle that shows up before earthquakes? No, I don't think the Hadron Collider can be used to predict earthquakes. Are photons the only massless particles, at least that we know of right now? No, gluons are also massless. I should jump down to the bottom because I'm way, way, way behind. Do physicists believe in God? Some of them do, some of them don't. When radioactive stuff gives out gamma rays, what's going on? Unlike alpha or beta, gamma isn't clearly a part. Oh, yeah, so the thing about, I mean, beta rays are also not a part of the nucleus, right? So like you have a neutron decay into a proton, an electron, and a neutrino. But a similar thing is a closely related thing is happening for gamma rays. For gamma rays, what's happening is that the same number of neutrons and protons are there, but the neutrons and protons are dropping into a lower energy state because they were excited for whatever reason. From Angelus with the 20 pounds, thank you so much, Angelus. Why can't we use quantum entangled particles to get real-time data sent from, say, Mars by using lasers to move particles and observing the movement in an entangled particle using the original position as 1 and moved position as 0? So entangled particles don't transmit information, can't communicate information, just kind of by definition, not by definition, but one can prove that you can't send information via entanglement. And the point is that entanglement, the correlations that you see as a consequence of entanglement, they don't happen until after measurements are there. So you need to measure both sides and then compare them, and only then will you notice that there's a correlation. If you made a measurement, if you had an entangled particle on Mars and an entangled particle on Earth, say, and you measured the entangled particle on Mars, you wouldn't know that that's happened on Earth until you measure the one on Earth. And once you measure the one on Earth, you wouldn't know if the person on Mars has measured theirs until you compare, right? So you make a measurement on Earth, you make a measurement on Mars. Making a measurement on Earth doesn't tell you anything about what's happened on Mars unless you know that they've already made a measurement. And that's the issue. And you can't control what the outcome of your measurement is. From Kittenish with the $5. Hi, Dr. Blitz. What is the biggest problem in quantum physics? The biggest problem? Quantum physics is remarkably successful. Now, the biggest open question probably in the standard model of particle physics, which is just like a part of quantum field theory, is, well, I don't know if it's the biggest question, but one of the big questions is why neutrinos have mass, and trying to figure out what the masses of neutrinos are. That's a very, very weird thing. We don't know why they have mass. We don't know, like, their masses are extraordinarily tiny. Another issue is that we don't know why there's more matter than antimatter in the universe. We don't have a good accounting of how there's so much more matter than antimatter. And this is expected to be resolved via quantum field theory, but we don't know how to do that yet. Retrocausality says otherwise. There's no retrocausality in quantum field theory, or in quantum mechanics for that matter. How does gravity emerge from quantum information? Well, we don't know. This is an open question. It's not even clear if gravity does emerge. Why are pulsars and neutron stars depicted like they emit visible light? Shouldn't they look like gray, blurry iron spheres that if they only emit X-rays? Well, look, so depending on how new they are, they could be very hot, in which case they could emit visible light. In fact, I'm curious. Temperature of a neutron star. Yeah, so it depends. At birth, they are, almost 1 trillion Kelvin, and then they cool down to about 1 million Kelvin after a few thousand years. And then they eventually might cool down to hundreds of thousands of degrees. So yeah, they would definitely emit visible light because they're very, very hot. Can you explain light year and speed? I genuinely can't understand it. So light speed is just a speed. A light year, like it's like 300,000 kilometers per second. A light year is the amount of distance that something traveling at the speed of light can travel in a year, which is, it's like 1.2 trillion miles or something. Is it possible that the universe stop expanding, reverse, turn into singularity again in Big Bang? So that's not ruled out, but it's also not confirmed that it will happen. I don't get neutrinos. Are they just scraps of matter too small to further decay? Well, they're just one of the like 1 or 2 dozen fundamental particles that we have. How do particles of spin 2 exist? Well, if you slap together a whole bunch of so are we talking about composite particles or fundamental particles? Because composite particles, you can just have the spin of the composite particle be controlled by the angular momentum of the orbital angular momentum of the particles that compose it, of like the quarks that compose it, in which case you can have spin 2, whatever. Fundamental particles, it's not clear. If there is a graviton, then the graviton would have spin 2. From Truth Over Faith with the $10. Hey, Dr. Blitz, I heard about artificial retina being developed in zero-G and delivered to Earth. What are some other applications that can make use of the lack of gravity? Oh, I don't know. That's almost like an engineering problem. It's not something that I would know about. Sorry. It is neat, though. And I know that some things have been developed in... Well, some things have been developed for space. I don't know about things that have been developed in space. Yeah, I don't know. I'd have to think about it. Is it possible to get an intuitive understanding of what spin is? Not really, because it's not really like an intuitive thing. It's like asking, what is an intuitive understanding of charge, right? Like charge is just a thing that makes a particle behave in a certain way. Spin is a thing that makes a particle behave in a different sort of way. Did you do a dissertation? If you did, what about? Yeah, I have a PhD, so I must have. My dissertation was on conformal hypersurface geometry. Do physicists take neo-Lorentzian interpretation seriously? None that I've met. From Lukey T with the $5. Personal question, not really related. I'm a chemical engineering student and was thinking of Gibbs free energy as a tattoo. Yes or no? Chat can help. If you do chemical engineering, that seems like it's not the worst choice that you can make. Could you explain what lattice QCD is and what strange animation and that strange animation of empty space, please? So I can explain what lattice QCD is roughly. That animation of empty space I can't explain. I don't know exactly what they were actually simulating. I'd have to look into it more. I know what you're talking about though. So lattice QCD is a way of trying to do quantum chromodynamics or trying to solve quantum chromodynamics problems. Quantum chromodynamics is the quantum field theory that describes the strong nuclear force. This is the thing that holds protons together, that holds the quarks together in protons, that holds the quarks together in neutrons, and so on. And so one of the ways that you can solve these problems numerically, or perhaps even try to solve them analytically if you're really, really good, is that instead of trying, and so there's this problem called renormalization, it's not a problem per se, there's this difficulty called renormalization. And this happens in basically all quantum field theories, not technically all, but many, where essentially the system changes as you zoom and zoom, or the governing constants change as you zoom in more. And what that means is that the systems become very, very difficult to handle. And in particular, because quantum chromodynamics is also something called non-perturbative, meaning that the constants, the strength of the force is very, very strong, it makes it really hard to use our standard techniques to solve those kinds of problems that we would usually use for like electromagnetism, for example, because electromagnetism is fairly weak. So one of the ways that you can approach this is instead of kind of trying to use the analytic techniques that we typically do, what you do is you just put it on a grid, and then you see how the behavior and you can put it on basically a tiny grid, your problem, solve your system on the grid, and then try to figure out what happens as the grid gets smaller and smaller and smaller. And so you have a lattice, and you're solving the problems on a lattice. You're basically discretizing space. And it works. It works really, really well. From Fits of Rage with the $5, if I were going 99% the speed of light, would it look like I'm going faster than c since time dilation would have me experience less time than the relative time? No. From your perspective, you're always apparently stationary. From your perspective, the universe will shrink longitudinally, so you will get to locations faster than you would have thought you could get to them if you were going slower, because the distance between you and some location will get smaller. From someone else's perspective, they will see you moving at whatever speed you're moving at, and your clock will just appear to go slower. How does a neutron star get the spin going enough to be a pulsar? Yeah, so usually what happens is that you'll have a neutron star form, but it forms with so much angular momentum that it's already spinning extraordinarily rapidly. And the reason it forms with so much angular momentum is because maybe the star that formed it was already spinning pretty fast. The speed at which a star spins will depend on its formations, like what happened during its formation, how quickly was the gas cloud rotating, all of those things. And so if the angular momentum of the star was very, very large, if it was spinning very, very quickly, once it shrinks down, kind of like an ice skater pulling its arms in, it'll spin even faster. Is it true that if something goes at light speed, a black hole will be created? No, that's not true. Can you explain the Ricci tensor and the basis of it Gauss made in non-Euclidean geometry? I'm not sure what you mean by the basis of it. But so what the Ricci tensor is a measure of some kind of, depends on whether you're in space-time or just a pure space, but it's a measure of curvature. And the way to think about it, the way that I conceptualize it, the intuition that I have is, if you're at a point and you imagine shooting off cones, like take a point and then start making like a circular cone emanating from that point, right? so shoot off cones in whatever direction you want. The Ritchie curvature is going to tell you the growth rate of the surface, or of the area of the cone, as a function of distance in the direction, in some direction. The Ritchie curvature basically captures that idea. So if you take the Ritchie curvature, you plug in the direction twice, you will get information about the growth rate of the cone. From Captain Obvious with the $5, what are the technological and physics limitations preventing us from developing tech that could fold spacetime? Well, the physics limitations is that folding spacetime is like a nonsense thing. It's not like a thing that you can do. You can bend spacetime, you can warp it. Folding it implies something else that's just not possible given the known laws of physics. Furthermore, what you can do is you can bend spacetime sort of in one direction, but not in the other direction. You can bend it sort of down and not up, meaning that you can kind of cause spacetime to contract around something by putting something heavy somewhere, then spacetime will contract around it. But if you want to expand space, kind of like what would be required for a warp drive, you need something that has negative mass, which as far as we can tell just doesn't exist. So those are physics limitations. These aren't technological limitations. These are the kinds of things that just don't exist, at least as far as our physics is concerned. How does magnetism work at the quantum level? So at the quantum level, these fundamental particles, electrons, quarks, they have angular momentum, and they also have charge. At least some of them have charge. And the ones that, the angular momentum that they have gives them a magnetic field. In the same way that like a spinning amount of current, if you have current going in a loop that produces a magnetic field, these charges just have intrinsic magnetic fields because of their spin. And then if you stack all those on top of each other, you can get large magnetic fields. Do you account for higher dimensions in your work? Yes, I do, absolutely. You're not uploading these live streams to YouTube? Yeah, I am. They're on YouTube. They are literally live on YouTube. Why sometimes we can see the moon and the sun at the same time in the sky? Because sometimes the moon will be at a right angle relative to the, or sorry, not a right angle, will be at a, well, yeah, that can happen too. If you see the moon setting and the sun rising at roughly the same time, then you can see something like a full moon. And that's just because the moon is almost behind the Earth, but not quite behind the Earth. And the sun is on the other side of the Earth, and so you can see them both by looking in by looking in opposite directions. How is the island formula justifiable in asymptotically flat space without a boundary dual? I don't do anything with the with these kind of like what are they called? This is like, oh, I was thinking about this a few months ago, but yeah, I don't do anything with like computing entanglement entropies on boundaries or things like that. Like I don't do any of that stuff. Like that is more sophisticated ADS-CFT than I do. I do almost exclusively classical stuff. Highest math you've taken? I guess I took a functional analysis class when I was a grad student. From Angelus with the £5. Sorry if this is too personal, but how did treatment go? Good, I hope. Yeah, I mean, like, you should go watch the follow-up video I made. I made a follow-up video, like, I don't know, at the beginning of April or something. So you should go watch that. It's on the channel. Bottom line is, surgery went well. Everything's gone. I'm doing okay. I might have celiac disease though. That's not fun. But we'll see. I need to get evaluated for that. What about when the moon is almost next to the sun? Well, you'll never see the moon next to the sun. Well, what you can see is you can see the moon kind of, like the moon might be above during a sunrise, or the moon might be near the horizon during a sunset. In that case, then that just means that the sun is, and you know, they might be like 90 degrees apart or like 45 degrees apart. Basically, the closer the moon is to the sun, the more it is that it will be closer to a new moon. So you'll see less and less of it. Because if the moon and the sun are near the same place, that means that the moon and the sun are almost aligned. And when the moon and the sun are aligned, that's when you get a new moon. Do you think Rieman's hypothesis will be proven this century? I don't know. And it's Riemann. how do muons support special relativity, and how would atmospheric counts relate for assessment? Yeah, so the rough idea is that muons are unstable particles, right? They decay into electrons and electron antineutrinos after, or actually, I think don't they decay into pions? Yeah, I think they decay into pions. Muon decay channel. The muon decay channel is, oh no, I'm sorry, they decay into electrons and electron antineutrinos. I was correct about that. And then sometimes some photons as well. But the important point is that they have a fixed decay time. It's about 2.2 microseconds. And so if you just have a muon just hanging out, just slow, not moving quickly, it will decay in that 2.2 microseconds on average, if you can figure out what the decay constant is by measuring a bunch of them. However, muons that are extremely fast, well, because of special relativity, or because of, the muons that are extremely fast seem to decay much, much slower. The explanation being that there is time dilation happening. If you can come up with some alternative account for why muons decay slower when they move quickly, and the rate at which they decay is exactly accounted for by their speed, then you'd I don't know, win a Nobel Prize or something. The point is that muon decay rates, especially muons coming from the upper atmosphere, they decay at exactly the rate that we expect given special relativity is true, and time, which implies time dilation. What the heck is physicist even a word? What the heck does that even mean? You don't know what a physicist is? It's what Albert Einstein was. Can you imagine a way for communication using neutrinos? Not only can I imagine it, it's been done. It's just really inefficient because it's really hard to detect neutrinos. And so like imagine that you're trying to communicate with something that you could only detect 1 in a trillion or 1 in a billion, signals. If you have to learn about gravitational waves from the start, where do you begin and what's the path? Well, first you need all of calculus, you need differential equations, linear algebra, partial differential equations, and then once you do that, you can pick up a book called Spacetime and Geometry by Sean Carroll, and then you read through that book. A closed universe does a recollapsing electromagnetic wave self-gravitate enough to blue shift. Yeah, so if you have a recollapsing universe, then yeah, if the scale factor is decreasing, then the electromagnetic waves will blue shift. Yeah, that's a thing. Ice melting in water does not change the water level. Why is this different for the oceans? It's not different for the oceans. The reason why sea levels rise from ice melting is because you have ice melting on land, and then that water runs off into the oceans. From one man with the $2, what's the biggest ethical principle physics taught you? Physics doesn't really teach ethical principles. It's not really a thing. I appreciate the question though. I mean, but there's just not a lot of ethics involved in physics because we don't work with we don't do human experiments, right? Not really a thing. Is it LIGO that they were studying gravitational waves? Yes. You talk to guests only on TikTok and Discord, right? Yes, because there's no other way to bring up guests. At what age did you get your PhD? I was 29, or I was just about to turn 29. Are water pools the best way to detect neutrinos, or could you have many sheets of something denser? Water pools are great because the way that we detect neutrinos is by them basically kind of not deflecting, but doing like grazing off of atoms, mostly like atomic nuclei, or yeah, it's mostly atomic nuclei, I think. And so what that means is that, and then in that process, they lose energy and they create new particles, and those new particles then are zooming. Those new particles have extremely high energy, and those high energy particles are then zooming through the water faster than light can travel in that water, and that gives off light. It's called Cherenkov radiation. So you want something that's clear, and you want something that, yeah, so you want something that's clear, basically, and you want something that's fairly dense. Air doesn't work particularly well because it's not very dense. Water is about 1,000 times denser, and so there's not a lot of stuff that's easy to obtain a lot of and is also clear and dense, right? Can you explain the definition of temperature, one that involves microstates and entropy? So the definition of temperature is the rate at which the amount of heat you have to add changes as a function of the entropy of the state. Or put another way, it's the rate at which entropy changes as a function of heat added. That's the inverse of temperature. Now, once you know what entropy is, then you're done. So, you know, typically for a system, you add some amount of heat to the system thermodynamically, and then the entropy of that system increases. So temperature will tell you, the temperature controls how much the entropy increases as a function of how much you add energy, how much energy you add, rather. Is there any indication that space's expansion happens everywhere, whether matter is present or not? I mean, it seems to be that space is expanding everywhere. In fact, space seems to be expanding in places. Spatial expansion seems to only be noticeable where there's not a lot of matter. There'd be ethics if particles could scream true. You, as a physicist, how are you contributing to the advancements of science today? By increasing our understanding of the cosmos, of gravity, of certain mathematical structures. Is the wave function ontological or just epistemic to you? I take the view that it's ontological. Is it correct to say that comparing frames of reference between Earth and space isn't possible, delta V? You can compare reference frames. You can always compare reference frames. As long as, okay, so there is a sense in which you can't compare reference frames if space-time is sufficiently curved, but like neglecting the space-time curvature caused by the Earth's gravity, then yeah, you could compare reference frames, no problem. How is glass see-through? Because the light doesn't get absorbed and re-emitted. Do you believe that us as 3D creatures see in 2D, but our brain modifies it to make it appear as 3D? Well, in some sense, each eye picks up two-dimensional information, but we have two eyes, and you can combine two pieces of two-dimensional information to get three-dimensional information. What type of math are you using in applied physics? So I don't do applied physics, but the math that I use when I'm doing the physics that I'm using, when the math that I use when I'm doing the physics I'm doing is generally just differential geometry. Sorry, I have to jump down to the bottom because I'm way behind. How do we know the Big Bang happened 13.8 billion years ago if we don't know how big the universe is? So the 13.8 billion years is an inference. It's basically, look, we see how the universe is evolving now. We can see how the universe was evolving in the past by looking at distant galaxies, because distant galaxies, we're seeing them as they were, you know, however many million or billion years ago. And so we can use that information to determine kind of like the shape of the expansion curve for the universe. And this gives us data, like, you know, it's a little bit more complicated than that. We get some data, we use it to fit parameters and so on and so forth, and we have a model that we use to describe that evolution. It's called lambda CDM. But the point is that we take all this data, we fit it to a model, and then that model tells us what the so-called scale factor was as a function of time. And what we find is that the scale factor, if you take this model seriously and you apply it across all moments of time that it's applicable to, it says that the scale factor was 0, roughly 13.8 billion years ago. And that's what we call the Big Bang. Scale factor basically is how much is the relative size of the universe at time t relative to now. In a purely classical Yang-Mills field in Minkowski space evolve from smooth Cauchy data? I guess it depends on the Yang-Mills field. If it's just like a U1, if it's like a U1 Yang-Mills field, then sure. I don't see why not. I don't understand why you're asking the questions that you're asking though, Spear. Like, these aren't urgent questions, and most people don't just have this like curiosity for this random slew of highly technical questions that you're asking. So it feels like I'm being quizzed. Is it true that the constants could have been other values which allow life, disproving fine-tuning? Well, yeah. So definitely if the constants could have been any other values, which we don't know, then there are definitely some values that could still allow other values that could still allow life. So the question is just how large is the range of allowed values, and how does that compare to the range of allowed values that allow for life? relative to now, but we don't know the size now. Well, look, we don't need to know the size of the universe. We just need to know how much the universe is expanding or contracting, depending on which direction in time you're going. So like what we do know is we know that the observable universe was, you know, 1,000 times smaller 380,000 years after the Big Bang, roughly. You know, we know, like, there's this quantity called the Z factor, which it's a redshift factor, which tells you how much space has expanded between two time periods. And so, like, you don't need to know the actual size of space to know how much it's expanded. Why do we say that the universe expands if there's technically no space to expand to? It's not expanding. There's no edges. It's not expanding by the edges getting further away from each other. It's that every chunk of space is getting bigger. In some sense. What do you think about the law of non-contradiction? It seems fine. It seems like a good way of reasoning about things. How far are we from simulating QCD well enough to the point of predicting stable isotopes of heavy elements directly? Oh, I doubt we're anywhere near that. Why does manipulating quantum entangled particles not allow us to send info faster than light? Well, because you can't control what the outcome is of a measurement. And you can't, and when you make your measurement of an entangled particle, you can't know if the other person has made their measurement or not. So you can't tell, like, you get no information from making your measurement on your end. There's nothing that you can do. There's nothing that the other person can do to let you know that something has happened until you talk about it. I'm assuming you have published papers. What things do you talk about in those papers? Well, you can go read them if you go to my website, blitz.phd. If you go to my website, you can go take a look at all the research that I've done, all the papers that I've written. I talk about a lot of things. It's a lot of differential geometry. It's a lot of, it's, you know, a fairly decent amount of cosmology, some black hole stuff. Who created the universe? I don't think it was a who. If we reach the edge of what is observable, the center of the Big Bang also changes. Well, the Big Bang doesn't have a center. Why does light move at the speed it does? Like, why not move slightly slower or faster? If it moved slightly slower or faster, that would just mean the speed of light constant, which is just a constant of nature, would be different, which just means that the way that we define what a second is, the way that we define what a meter is would just be different. Like, this is just like the speed of light having the speed that it has is just a unit choice. Sorry, I have to jump to the bottom because you guys are asking tons of great questions. I appreciate it. Time is relative 13.8 billion years ago to who? Yeah, so this is a good question. So there is this idea called, there is this idea that time is relative in general relativity and special relativity as well. But that doesn't mean that the configuration of the universe doesn't lend itself to a nice, convenient, kind of universally agreed upon reference frame. We call this the co-moving reference frame. It's basically, if you were far away from any gravitational influence, it's basically the reference frame that you would have if you were stationary with respect to the cosmic microwave background radiation. So there's radiation coming in all directions. And depending on how you're moving relative to the cosmic microwave background radiation, what the direction you're moving in will look blue, the direction you're moving away from will look redder. So if you pick a velocity so that it looks the same in all directions, that would be a co-moving reference frame. And so it's the 13.8 billion years is relative to that reference frame. From Kate Eilert, or Eilert, do all nanoparticles have ability to adjust attributes like twisted angle as with graphene? Oh, I have no idea. This is a condensed matter thing. I don't do condensed matter. But to be clear, graphene isn't a nanoparticle. So I'm not sure what you mean by that. But again, not a condensed matter physicist. One thing that's interesting that people don't know is that if you're a physicist, most physicists are not going to know much about, except like what you might learn in grad school, about things outside of their particular subfield, right? So I do relativity. almost exclusively classical relativity. And I dabble in some quantum stuff, right? I dabble in some quantum field theory and curved spacetime. I dabble in some, sort of like high energy theory. So like I talk about, some, new fundamental fields and, the Lagrangians and things like that. But that's like a dabbling. And so like, I know almost nothing about condensed matter stuff, like very, very, very little about it. The only things that I know about condensed matter stuff is stuff that I've learned because I wanted to make videos about these things. I don't do any research that has anything to do with anything condensed matter. I didn't learn any of that stuff in grad school. So it's like, I apologize to the people who ask questions about things that I just don't know the answers to, but I'm not gonna make something up. Are wormholes possible? Not the ones that you see in science fiction. How do we measure speed of time? Well, all you can do is you can compare clocks. You can compare my clock to your clock, for example, and see whose ticks faster, for example. I think they mean graphene has the properties of a nanoparticle. Maybe that's what they mean. Have you discovered anything new? You'd have to go read my papers to find that out. I mean, in some sense, yes, but it depends on what you mean by discovered. Most mathematicians are Platonists. Are you? No. That's why I'm perhaps more of a physicist. Why does the total angular momentum need to be preserved, but not spin orbital angular momentum? Well, total angular momentum is the thing that's associated with the symmetry. Sorry, with rotational invariance, right? So the conservation laws are derived from symmetries, and the symmetry that gives rise to angular momentum conservation is rotational invariance, meaning that if you rotate your coordinate system, for example, the Lagrangian doesn't change. And there just is no such symmetry for specifically spin or specifically orbital angular momentum that conserves those. Other than teaching, how do you make a living? That's how. That's how most scientists make a living. Depending on what they're doing, of course. Some will just get grant money for research and then they won't have to do that. They won't have to teach. From Chase with the $5, if you had to wager, would you say at least one more spatial dimension exists? My obviously biased opinion is at least one more exists. Honestly, I wouldn't. I probably wouldn't take the bet either way, to be honest. I would just be like, I don't know, man. Do you think there's a possibility of faster than light travel physically, not just theoretical? No, I don't think so. What were the first particles that resulted from the Big Bang? Well, so quarks, leptons almost certainly existed very, very early. I mean, gluons would have existed very, very early. Basically, all of the fundamental particles would have been there, with the exception of photons and the W and Z bosons. Those things didn't exist until after the spontaneous symmetry breaking from the Higgs. But yeah, there's no reason to think that quarks and leptons and gluons wouldn't have existed very, very early on. Please explain matter, antimatter, and dark matter. So matter is just the stuff that you're used to today. It's just the things that make up stuff, like the things that make up this piece of plastic stuff. It's matter. Antimatter is very much like regular matter. It's very much like matter, except almost everything about it is flipped. So if an electron, which is a kind of particle that makes up matter, if an electron has negative charge, then an antimatter electron will have positive charge. The only thing that stays the same as far as we can tell is the mass. The mass is unchanged. Now, dark matter is something completely different. We don't even know what it is. It could be a kind of particle that is heavy, but it just doesn't give off light, so we can't see it. But it could be just like microscopic black holes. It's just something that has gravity, but we can't see it. From Unbathed with the $10, I remember reading an estimate of the recurrence time for the local universe as 10 to the 10 to the 10 to the 57 years. I'm not troubled if the estimate is off by tree 3 because time flies while I'm dead. Yeah, so I haven't seen this particular estimate, but for the observable universe at the size that it's at right now, the recurrence time would be truly enormous because the universe is truly enormous. So the phase space or the configuration space, well, I guess phase space is appropriate. The phase space is truly enormous. However, if the universe was much, much smaller, then the configuration space could be much, much smaller, and so you could have recurrence happening in much, much shorter amounts of time. How do you feel about superdeterminism to solve Bell's theorem? I mean, it does solve it, I just don't like it. Tuesday, let's debate flat Earth. Nope, not on Tuesdays. Do you think a divine creator created the Big Bang? I don't. What happened to the black hole that formed early in the universe? It's not clear that any black holes did. We're working on it. People have proposed these things. They're called primordial black holes, but this is not something that we've had compelling enough evidence to say that they definitely exist. From Nectu with the $5, do you think that caller on UA this past weekend, Matthew Marshall, might have been trying to talk about aseity and was confused calling it ality? Maybe. Well, they definitely weren't conveying that idea. From Chase Martin again with the $5, just wrapped up a paper on Casimir-like effects of strings between two 5-branes for the hierarchy problem. Even in 5D, the elegance is shocking. Yeah, you do get a lot of nice things if you ramp the dimension up, if you allow for like higher dimensional things, but also keep in mind you're also doing strings. Strings, like even if we were to grant that higher dimensions exist, that doesn't necessarily then imply that strings exist. But yeah, I mean, like there's a lot to be done and a lot to say, and I do grant that string theory is extremely elegant. Darmok and Jalad at Tanagra, indeed. Shaka when the walls fell. Has antimatter ever been contained, and how? Yeah, we contain it actually pretty regularly, and we contain it using magnetic fields called magnetic traps. And I think they also sometimes use electric fields as well, so like maybe they're called electromagnetic traps. Least favorite topic of physics for you? Probably condensed matter stuff. Are you a dual aspect monist? If I knew what that was, maybe I'd have an answer. I don't know what it means to be dual aspect as a monist. Can I come up? I have a question. Not yet, no. Did anybody watch the series Dark Matter? It was creepy. I did. I actually liked it. Have you heard of the local friendliness no-go theorem? No, I haven't. From Chase Martin Physics with the $2. True, Susie is a bigger problem than dimensions. Yeah, exactly. Susie is a big problem for string theory, and honestly, I would be a lot more on board with string theory if Susie was detected at the LHC. Is matter essentially electrical charges? No, not all matter is electrically charged. Is it possible to teleport? Probably not. At least not in the sense that you want to. Why are neutron stars so dense? Essentially, they are what's left over from a star that has fused all of its core fuel into iron. But it turns out if you take a big enough clump of iron, and you collapse stuff onto the surface of that clump of iron, it'll send a shockwave through that compresses it more and reaches another stable state, which is the neutron star. Could we use quantum entanglement to allow us to gain information from inside a black hole? No, you can't learn anything about what's going on at the other side with quantum entanglement. It doesn't transmit information. Is it true gravity waves travel the speed of light? Yes, as far as we can tell. Have I watched Backrooms? No. Why don't you like condensed matter theory? I don't know. It just seems condensed matter theory feels a lot like real analysis to me. And then it seems like that there's just like a lot of tricks that are kind of ad hoc. And I don't know. And again, maybe I'm talking out my ass here. But something about it just like, A, it's not particularly fundamental. And, you know, I'm a sucker for fundamental physics. But B, something about it seems like, it seems messy. Right? From Space Barbarian with $5, I heard astrophysical black holes described as spinning. What does spin do to things like the event horizon singularity and mass distribution? So we have no idea if singularities exist. If they do exist, a spinning black hole has something called a ringularity rather than a singularity. So the singularity is smeared out over a ring. However, spinning black holes do exist, and as a result, their event horizons are not perfectly spherical. They're more shaped like oblate spheroids. So, you know, there's like a genuine top and a bottom, and it'll be like, you know, you can get closer to the top and bottom than you could get to the edges. It also produces a thing called an ergosphere, which is a region of space where basically you can't help but rotate with the black hole. So that's an interesting feature that non-rotating black holes don't have. But we don't know anything about the mass distribution within black holes. So from Angelus with the 10 pounds, thank you so much. Given black hole, take in matter and spaghettify it. Does matter get broken down to its base atoms, e.g. wood to carbon, water to hydrogen? It would get broken down into its base particles. So the carbon atoms would get broken down into, you know, electrons, neutrons, and protons, and then the protons and neutrons would get broken down further into their constituent quarks. But no, they're not. So atoms would not survive a black hole. But again, to be clear, there's not really, in my view, not really good reason to think that there are actual singularities in a black hole. Are black holes' event horizons a causal boundary between matter within and outside the black hole? Yes, that's what defines an event horizon. What is SUSY and how does it relate to string theory? So SUSY is supersymmetry. It is a particular kind of, it's called a symmetry. It's a way that you can transform the mathematical description of a physical system. And, you know, if supersymmetry is true, then the physical system, the physical system would have nice properties after you do this transformation. One of the implications of superstring theory, if it's true, is that every matter particle called a fermion has a bosonic partner pair. The bosons are typically things that like convey forces, or they convey mass, like the Higgs boson, but they have a different kind of spin. And so the point is that if supersymmetry is true, we would expect a lot of new particles that we haven't seen before. And in order for string theory to work, you have to have supersymmetry, at least in the versions of string theory that I was taught when I was a grad student, because otherwise you just can't make matter. There's no explanation for why matter particles exist in bosonic string theory, because all you have is bosons. You don't have strings. You don't have fermions, and matter particles are made of fermions. So you need supersymmetry for string theory to work, to represent our universe. And as far as we can tell, supersymmetry just doesn't exist. Like, we've done experimental tests, and at least it doesn't exist where people thought it would exist. Now, maybe it exists at much higher energy. That's hard to say, but ask you about the black hole. You said a ring of singularity. Why not a sphere of singularity? It's not a ring of singularity. It's called a ringularity. Just replace the S with an R. And it's a ring because it's rotating, and that's the that's what you end up showing if you try to calculate what the configuration of the singularity is for a rotating black hole. It forms a ring. And I mean, think about it this way: a spherical shell singularity. Well, that would have the top and bottom of the spherical shell. They wouldn't be moving, so why wouldn't they collapse in more? They wouldn't have like any reason to be pushed away. A ring, on the other hand, would have kind of the centripetal or the centrifugal force pushing it outward, stretching it out in a ring shape. From Blancs with the $5, no question this time, just happy to support. I guess thoughts on the CERN shutdown? Well, thank you so much for the support, by the way. My thoughts on the CERN shutdown are pretty straightforward. I think that, like, I'm excited to see what will happen next, because I know that they're shutting it down for an upgrade. I hope that the upgrade gets us a whole lot of new data, and that'd be really exciting. And from Chase with the $2, you're right. Also, we need SUSY to get to 10D. That's true, too. Yeah, otherwise you could have 26 dimensions, I guess. False men. I'm a physicist. Your explanation of sussy, it's false. No, it's not. But okay, whatever you say, man. What's a physics fact that actually unnerves me? Nothing unnerves me. No physics facts, anyway. If a neutron star captured a planet again, or kept an old one, would it have a Goldilocks zone where liquid water could be? I guess in principle it could. But liquid water wouldn't mean that life could exist, because you'd still probably have a ton of gamma rays. What is the microscopic origin of black hole entropy? This is an open question. We don't really know. String theorists will tell you it's stringy stuff. Loop quantum gravity people will tell you it's loopy stuff. But we don't know. This is an open question. Does Hawking radiation come from a black hole or from around the event horizon? This is a good question. It seems to be the case that you need an event horizon for Hawking radiation to happen. So even though you can't localize the Hawking radiation as happening right at the event horizon, it seems like if there is no event horizon, just like around a neutron star, there will be no Hawking radiation. So the event horizon plays a role, but it's hard to say whether you can localize the Hawking radiation to happening at the event horizon. Is glass in a liquid state? No, it's just amorphous. What is action in the least action principle? Action is, at least classically, action is roughly kinetic energy minus potential energy. There isn't really a good explanation as to why that kind of thing gives rise to good equations of motion. It just happens to do so. And to be clear, usually what happens is that we have some equation of motion that we want to describe, and then we try to come up with the action that actually, or whose variation from the least action principle gives you that equation of motion. The action is generally not something that is like fundamental, that has like some physical explanation, except in the quantum setting. In the quantum setting, the action controls essentially the rate at which the phase of a quantum system evolves. I made a video on that a while ago, so you should check that out. You think that the quantum fields are made of something? No, well, okay, I'm not sure, but if the quantum fields are fundamental, then they're kind of definitionally not made of something. Is the event horizon just absence of light? No, the event horizon is a boundary between the inside and outside of a black hole, and that boundary is defined by the region beyond which, if you're inside, you cannot get out. How will we deal with the radiation when colonizing Mars? Probably big shields. Oh. Dual aspect monism means the underlying substance of reality is neither mental nor physical. Agree? No, I don't agree. How can we take any of you seriously when you don't know what 95% of the universe is made out of? To be clear, that's not true. We can say it's dark energy and dark matter is most of it. But like the world isn't, like there's plenty of stuff that we can know. Like we know how dark matter behaves gravitationally. We know how hadronic or how baryonic matter behaves quantum mechanically. Like there's a lot of stuff that we know. It just seems like that you're a science denier though, and you just don't want to, you know, pay attention to science because it's too complicated for you. What if spacetime has a maximum amount of realized curvature it can achieve approached asymptotically? What if? Is charge the only globally conserved quantity? Well, we call things charges when they're globally conserved. Angular momentum seems to be globally conserved. Momentum seems to be global, or translational momentum seems to be a conserved quantity. Charge, all the charges, in fact. Who is Murno Sleep? Why is this person saying Murno Sleep? Stop spamming. As a math PhD student, I studied GR and gauge theory, special holonomy manifolds, G2 Kalaba Yao. Ew, you do G2 stuff? Always interested in learning quantum gravity stuff. Any recs for someone with my background? No, I kind of picked it up as I went. It depends on what kind of quantum gravity you want to do. So there's kind of like canonical quantum gravity stuff, which is probably closer to the kind of thing that you'd be interested in. I don't know of any good books for this. I've just picked it up kind of by reading stuff, like reading papers and finding lecture notes, and like reading like a section of a chapter here and there. Canonical quantum gravity stuff is like the Wheeler-DeWitt equation, and you'll find a lot of that in the cosmology literature. Then there's like string theory quantum gravity stuff, or loop quantum gravity, quantum gravity stuff, and these are like specific models of quantum gravity, which you may or may not be interested in. Those are going to have textbooks on them that you can pick up. If you do GR and gauge theory and special holonomy manifolds, then string theory might not actually be that bad for you. So, you know, maybe if you're interested in string theory, you could just go pick up I think Polchinski wrote a book on string theory. I think that's the book I used. You could just go pick up a textbook and start going through it. I'm sure you'd probably be fine, as long as you have a decent-ish background in quantum field theory, which you might need first. Jumping down to the bottom, jumping down to the bottom. Is gravity actually a force, or it's the curvature of space-time? Well, look, it's not really clear how we define what a force is. So classically, a force is the kind of thing that can change the momentum of something. Gravity does that, right? Gravity can cause changes in momentum. It can cause momentum transfers, for example. Now, gravity is also a force in the sense that it is a curvature of something. In quantum field theory, the way that we describe all of the other forces is in terms of curvatures of things called principal gauge bundles. And so in that respect, every force is a curvature of something. Gravity is just the curvature of spacetime, or rather, more specifically, it's the curvature of the tangent field. Or even more specifically, I should probably say that it's the curvature of the, sorry, not the tangent field, the tangent bundle, but even more specifically, I should probably say it's the curvature of like a frame bundle. But yeah, GR is, at least in modern parlance, GR is absolutely a force. But we don't really use the word force to talk about physics anyway, except at like a lay level. Do you think the spinner approach to GR is useful, twisters? So I'm actually going to a twister conference this like at the end of the summer, and even though I've tried very, very hard to understand twisters, in fact, I went to a conference like 2 years ago to try to understand twisters better. And at that conference, Roger Penrose was talking, and Roger Penrose is kind of the inventor of twisters. I still don't understand them. So I'm sure it's useful, I just don't understand it well. From Chase Martin sending $5, a first course in string theory by Zweibach is a great start if you do not know about QFT going in. If you do know QFT, Polchinski is better. Okay, that's fair. How do virtual particles exist out of nothing? Virtual particles don't exist. It's made up. Hoopla. They're not real. Do you believe the 11 dimensions exist in order to justify string theory? No, I don't. I'm not a string theorist. Also, string theory gets you 10 dimensions. M theory gets you 11. Who has a chance of being more real, Doctor Who or Doctor Strange? Probably Doctor Who. Doctor Strange just has straight up magic. Yeah, Yang Mills exists. Yeah, the point is that Yang Mills is just curvature. And so those forces that we call Yang Mills theories or gauge theories, those are like quantum chromodynamics. That's a Yang Mills theory, and that's a curvature. It's described by a curvature. If virtual particles are hoopla, how does Hawking radiation work? I have a video about this, but the best and least hoopla explanation I've heard for Hawking radiation, aside from just doing the calculation and like really what it is this is just a feature of quantum field theory in a curved background. But the best explanation I've heard is that you can think of Hawking radiation as happening because quantum fields are tunneling from the inside of the black hole to the outside of the black hole. Is there a consensus on whether gravity is an emergent property or an intrinsic property? There is no consensus on that, no. I'm tired of this Grand Blitz. That's funny. Do you think planets like Proxima b could contain human life forms? Probably not human. You said you enjoy geology, so I guess you have a favorite rock or mineral. I enjoy geology in that I like looking at pretty rocks, and I think that the ideas are interesting. Do I have a favorite rock or mineral? What's it called? Hold on. I know that. So what? Fool's gold, and I'm forgetting the name of the pyrite, that's what it is. Iron pyrite. Iron pyrite is so neat because of the symmetric shapes that its crystals can make. Let me show you. Like these are just this is so crazy. It's crazy that this is real life. These are just like real natural crystals. They're just like perfect cubes. Like what do you mean you can just wander around in a cave and find this? What are you talking about? This is just a rock. Those are like maybe a centimeter across. Like here's another one. You can just find this shit in a cave. And that would be like half the size of a tennis ball. Roughly, at least that's what it looks like to me. Like it's just nuts that that's a thing. Like it's honestly, it honestly looks fake. But you can just find them. Yeah, here's another one. And this has a hand for scale, so like like what's going on there? Yeah, if anybody tells you that nature doesn't do straight lines, just show them iron pyrite. What was that cube? That's the iron pyrite. Could you explain briefly quantum Riemannian geometry? Probably not as well as the person who like invented it, but essentially it's just taking the it's taking the algebraic structures. So okay, let me back up. You can define manifolds just by talking about the functions on those manifolds, or more specifically, you can define geometries by talking about the functions on those geometries, and you can then talk about operators on those functions and so on and so forth. And so all you're doing, and this is my understanding, again, I don't have a great understanding of quantum Riemannian geometry. I kind of used results from someone else's quantum Riemannian geometry to do some quantum gravity stuff, but my understanding is that basically the normal like commutation relations that you would take for functions, for example, you just loosen those so that they don't necessarily commute. So you can impose algebraic structure on the space of functions, and then you can define one forms. Those one forms would be, you know, the exterior derivatives of non-commuting functions, and then you can build up the like a quantum Riemannian geometry in that way. That's my understanding, at least of the kind that I used in the paper that I wrote with Sean Magid. From Git Stanfield with the $5. Can you break down Lagrange in physics for laymen? Is Lagrangian mechanics used for general relativity as well? Thanks as always. Yeah, so Lagrangian mechanics is used basically everywhere. To summarize it, what a Lagrangian is it's a integral over the entire configuration space, if you will. In the case of spacetime, it'd be an integral over the entirety of spacetime. In the case of in the case of a single particle moving through space, it would be an integral over all possible paths. Sorry, I'm thinking of path integral stuff. It'd be an integral over time for a trajectory. So for a given trajectory, you would integrate along that path for the you would integrate essentially the kinetic energy minus the potential energy along that path, and it would the value of the Lagrangian would depend on what path you're using as an input. But the point is that the Lagrangian essentially associates to a trajectory or the dynamics of some sort of system, whether it's a particle moving through space or whether it's space-time evolving itself. It associates to a trajectory a number. And the idea behind a useful Lagrangian is that you want your equations of motion to be precisely the equations that you get when you try to extremize the Lagrangian. So once you're on the correct trajectory, changing the trajectory a little bit shouldn't change the value of your Lagrangian at all, or at least not significantly. So that's the idea. You think of it like the equations of motion for some system. So the equations of motion would be like F equals ma. The equation of motion for a system is achieved on some trajectory, or the equation of motion is found or is satisfied when the trajectory matches that equation of motion, and that trajectory is the trajectory that minimizes or extremizes the Lagrangian. I don't know if that helps. It's probably not a good description for a layman. But the Lagrangian is there's not like a good physics intuition for a Lagrangian, because it just assigns a number to a trajectory, and the number is extremized. It's not made smallest, it's extremized, when the trajectory is the physical trajectory. Is the Lagrangian similar to a function space inner product? It doesn't have to be. You can sometimes build Lagrangians that way, but it doesn't have to be. That's what this guy does, just looks shit up quickly. You would hear me typing. This is what my keyboard sounds like. You would hear it if I was looking anything up. Is it really possible to pass through something by quantum tunneling? Well, not for like people, but individual quantum particles can, yeah. They can and they do, actually. Should all the equations of motion in every physical paradigm be things that can be derived from action? I think that there's a theorem. In fact, yeah, this is just true, isn't it? Was it Gibbs? Or was it Helmholtz? It's one of these old physicsy mathy types. Showed what conditions are necessary for some equation to be the variation of a Lagrangian. And so the answer is basically no, not every equation of motion. Oh, in every physical paradigm. Well, maybe you could say that, like, for all physical systems, you should be able to derive its equation of motion fundamentally from an action. That is more believable, but it's just not true that, like, there are equations of motion that you could in principle write down that just are not obtainable from a Lagrangian, as far as I know. From That Guy Miller with the $5. So obviously every action has an equal and opposite reaction, but like why? Why when I throw a wrench in space does it throw it back? Does it throw me back? It's conservation of momentum. So all of Newton's laws are conservation of momentum in disguise. So Newton's first law says that a single object's momentum is conserved, meaning that if it's at rest, its momentum is 0, so it stays at 0. If it's in motion, it stays in whatever motion it's in, and so it doesn't change, it moves in a straight line. Newton's second law says that momentum can change when a force is applied, and that if there is no force, then there is no momentum change. And the third equation just says that if you have two objects that are interacting, the total momentum of that system must be conserved. And so if, for example, one interaction would be you throwing a wrench. When you throw a wrench, the wrench's momentum increases, so your momentum has to increase in the opposite direction. What is diopter? A diopter is a measure of focusing power. So when you're studying optics, there is something called the lens equation. Sorry, the lens maker's equation. Oh god, it's been so long. The lens maker's equation depends on the inverse of the focal length in a lot of places. Inverse distances show up a lot when you're studying optics. And this is because the curvature of a lens is, you talk about the curvature of a lens in terms of the inverse of its radius of curvature. So anyway, and so diopters are basically a shorthand or a way of describing the kind of focusing power, which is the inverse of the focal length. That's roughly what it is. I should probably jump down because I'm a bit behind. Any recommendations to relieve nausea? I don't know. Go see a doctor? As a sum of individual particles, could I quantum tunnel my individual parts? Groups of particles do show quantum interference. Yeah. So you could, but the probability is astoundingly close to 0. I made a video about this where I computed the probabilities, and it was so like, and I was giving like a conservative estimate, and it was so close to 0 that it'll never happen. In the wave function, why is the phase kx minus wt and not kx plus wt? Well, the idea is that you want, if the wave is traveling to the right, then that means that when the time is large, you want to have to be further to the right in order to be at the same phase. So if k and x, if the wave is traveling to the right, that means that as the time ticks forward, the x value also increases. And so kx minus wt can stay unchanged for the, can stay unchanged if you increase the distance at the speed that the wave is traveling. And so the phase will move to the right. However, if you have kx plus wt, that just means the phase moves to the left, or that the wave moves to the left. I just had the lens maker's equation in lecture today. Oh, well, what a funny coincidence. What do they mean by observe in the double slit experiment? Like, are their eyes closed at first? I made a video on this quite recently. You can check it on my TikTok page. But essentially, observe just means interact. Take a big thing, like a big object, like a device of some kind, some instrument, and use it to interact with the with whatever's passing through the double slit. Can you explain the equivalence principle in general relativity? Yeah. Roughly, the equivalence principle is that you cannot feel gravity. That if you were floating around an empty space in a closed box, you wouldn't be able to tell whether you were orbiting something or whether the nearest gravitational mass was 1 trillion light years away. You wouldn't be able to tell the difference. That's the rough idea behind the equivalence principle. What's a good intro into physics without college? I'm a poor blue collar person. Well, look, so college might not be free, but textbooks can be. So it depends on what level you're at. It depends on what level you want to learn. But you can find most of the university textbooks online for free if you're willing to raise the black flag. Just saying. Not that I would ever advocate for that, because that's illegal. But, you know, who am I to judge you for what you do? From what properties is time emergent? It's not clear that it is. This is not a consensus. What makes us not phase through floors? Well, there's kind of two pieces. One, electrons don't like to be near other electrons. Well, that's the main reason. And the reason they don't like to be near other electrons is, one, there's electrostatic repulsion. So electrons repel other electrons, and that's what makes up chemical bonds, is electrons buzzing around. And two, electrons don't like to be in the same state as other electrons, and that includes location. This is from the Pauli exclusion principle. Why do you need 3 levels in a laser rather than 2? Can the photon not laser through with 2 levels? Yeah, so the issue with 2 levels is that the excitation time and the decay time are going to be the same. And so you just can't, like, basically you need a decay that gets you to a metastable state that can last long, so that you can pump enough energy in to keep them all in the excited state. Although I guess in principle you could make a 2-level laser. You just need like a, it wouldn't really be like, you would have to be like constantly pumping to keep. Yeah, the thing is you'd have to pump with the same energy with the same frequency, whatever it is, that it gives off. So it just might not be that helpful. How do you reconcile the equivalence principle and spaghettification? Yeah, so the equivalence principle only applies at a point. So it only applies ultra locally. Spaghettification is a process, or is a consequence of the tidal, like T-I-D-A-L, tidal forces of gravity. So if you have 2 points that are not exactly at the exact same place, they're separated by some distance, the gravitational pull on one can be slightly bigger than the gravitational pull on the other, and that will cause a tendency to stretch. So in the real world, you could tell a difference by measuring the relative by measuring, say, stretching forces, or how much stress is put on, like, say, like a spring or something like that, because maybe one side is being pulled slightly stronger than the other side, and so it would tend to stretch. But that's because it's an extended object, not because the equivalence principle is false. How successful are extensions of the Einstein field equations involving higher order properties derived from the metric? So some of them are successful, but the thing is, and some of them are even quite nice because they get you to renormalizability, but it's not clear that they are going to accurately represent the world around us. And the more complicated they get, like the more, like, the higher order terms they include, or the higher order polynomials they include, the more complicated it is to find solutions, and to, like, prove things like uniqueness, and to show properties like inevitable collapse and things like this. So it's much harder to test these things against observable reality, and they also become more and more ad hoc. So successful is not necessarily the word I would use, but perhaps fruitful might be the word. From Bacon with Bush with the $20, thank you so much, Bacon and Bush. Bear with me, please. Would it be possible that there were a fifth dimensional thing, a fourth dimension that is at right angles to the XYZ axis and true access to time, both directions at will? I don't think it could interact with us. So 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 we are fourth dimensional things. Like we are four-dimensional things. We exist in 3 dimensions of space and 1 dimension of time. A fifth dimensional thing, if it were at all like us, would just be something that exists in 4 dimensions of space and 1 dimension of time, and it would experience time in the same way that we would. There's not really a way to make a being that has true access to time if they're within a space-time, right? If there's a time, then you don't have true access to it in the way that you might like. From Git Stanfield with the $5, how come other elements don't have the same potential to have the same kind of chain reaction like uranium-235? Is it because of the number of neutrons? Well, so they do. They're just not common. So uranium-235 is like it's one of the heaviest isotopes that there's a lot of. So it's easy to get a lot of it. You could get a lot of like neptunium, right? And I guess neptunium, well, I mean, the other example is like plutonium, right? Like we do this, you could do this with plutonium as well. The trouble is that what you want is something that's unstable to, say, neutron bombardment, but is otherwise fairly stable. So like there are a lot of heavier elements that are heavier than uranium that just don't last very long. It'd be hard to make like a chain reaction device out of them because they decay so quickly on their own. Uranium-235 lasts over 700 million years with a half-life of over 700 million years. So you can make a bomb, for example, out of uranium-235. On the other hand, it has to be unstable enough that if you shove a neutron in it, it completely destabilizes and then splits in half. And so you have to have, so uranium happens to be near that sweet spot. I guess there are probably other elements that do it, but I suspect that there just aren't other elements that do it as well. And from Bacon and Bush again with the $5, I'm working on a fleshed out atheismo for personal reasons. Oh, okay, well that's interesting. Aren't larger nuclei less stable? Yeah, exactly. So it'd be hard to like put them in like a bomb shape. Why is the Navier-Stokes equation so hard to prove right or wrong? Well, it's not a question of proving it right or wrong. It's a question of proving like uniqueness or existence and uniqueness and, you know, global existence, right? And that's hard because it's a horrible nonlinear differential equation, and nonlinear differential equations are hard. I understand spaghettification is the reality from an object's falling perspective, but from an outside observer, would you see a compression due to time dilation going to infinity? So you're saying, would you see them like get compressed because like one end isn't falling in, but the other end still is? Yeah, probably. But like just think of like trying to drop like a really long steel, well, yeah, imagine trying to drop like a really long steel rod into a supermassive black hole. So the tidal forces are very, very weak. Well, surely as the front enters the black hole, from the outside perspective, it'll just stop at the event horizon and disappear. But the back will still be falling in, right? And so yeah, I can imagine that you'd see compression. I'd have to work out the details, but yeah, that seems plausible. From the Rabid Squirrel Sage with the $2, all hail the emissary of the lava lamp. All hail indeed. Could gravity be a fluidic response to local field depletion? I don't know. How was the root canal? I think they did a good job. I'm still having some sinus issues, so like I haven't had the crown placed yet. Is my nose okay? It has a scar on it now. Why a black hole's surface area the size of its event horizon is more important than its volume? Well, I don't know if it's more important, but it definitely shows up in the equation for the entropy of a black hole. Now, why that happens, there's a lot of speculation about why, but ultimately it seems like it comes down to some sort of duality between like higher dimensional spaces and lower dimensional spaces. That, if I had to guess, it would be something like that. All right. So it is 10:30, And 10:30 means that I'm going to take the live stream and I'm going to convert it to members only text questions. Everybody can watch though. Members only text questions, and I'll also take guests to ask questions verbally. So I'm going to have to restart the live on TikTok, but I will be right back. And I will just take a minute to adjust that over on YouTube as well. So I'm going to end the live and then I'll be right back. So feel free to come back and listen to people ask questions. Anybody can join and ask questions. Ask your own questions if you're a member. And I will see you guys in a second. Just setting this up. Give me one mo. All right, we are set up. This is a perk that I've added for subscribers, for members and so on. Everybody can, everybody can watch, but normally I would end the live stream now, but I figure I extended about an hour and a half for people who help support me, which is very much appreciated, of course. So we're back on TikTok, so the TikTok viewers absolutely can hop in and ask questions if they have them, of course. If they don't have them, then they don't have to ask them. Have you ever thought about working with Professor Dave, Dr. Blitz? It's come up once or twice, but it never ended up, nothing ever ended up coming of it. And Git Stanfield, welcome to the membership. I'm surprised that you weren't already a member, considering how frequently you support me, but welcome. Thank you so much, Git Stanfield, as always. And Humble Lee as well, becoming a member. Very much appreciated, Humble Leo. You're very, very generous. Welcome, welcome. All right, we'll let people stream in on TikTok. And yeah, so if you have a question, oh, actually, let me turn on the URL as well. So anybody you can join Discord and you can ask me questions there. And if you're not on TikTok, of course, or you can hop on TikTok if you want to ask me questions on TikTok. You thought you were fair enough. Taran Taha Ali, thank you for joining. I appreciate it. I appreciate you guys supporting me. It's all very much appreciated. All right, let me hydrate a little bit. I definitely had a gift sub at one point, but we're back. Yeah, fair enough. And by the way, if you become a member, your question is basically guaranteed to be answered because there are fewer questions. Would a hollow black hole cube block a very strong magnet? I'm not quite sure what that means. A hollow black hole cube? You can't really make a black hole cube. I also don't know what it would mean for it to be hollow. I was here. Welcome. I appreciate it. What's a recent cool discovery in the field? I mean, look, like discoveries happen all the time, so it's really hard to say like what's like the big recent cool discovery. I haven't seen anything that particularly caught my eye recently, like in the last week. But probably the biggest thing that we did as a field collectively in the last 10 years was finally we can observe black hole event horizons. Or not black hole event horizons, but we can observe black holes directly with the radio, like in the radio wave part of this electromagnetic spectrum. That was really neat. That was in 2019 and 2022, if I remember correctly. Hollow black hole cube, the most famously dense thing in the universe being hollow. Exactly, yeah, right. Like I don't know how that works out. What's the relationship between entropy and time? It seems like one of the ideal ways of telling time passed is a change in entropy. Yeah, so it's not quite clear what directs the flow of time, like why time seems to go in one direction than the other. The best explanation that a lot of physicists have to offer is that time flows in the direction of generally increasing entropy. That's it. That's the whole thing. that time is actually more of an emergent thing from entropy, from the direction of increasing entropy than anything else. I didn't know Professor Dave really doesn't like Sabina. A lot of people don't really like Sabina because she's really like, I don't like how cynical she is. Like, she's really good at explaining a lot of physics, but she's really cynical. Trouty, welcome to the party. Thank you for joining. I'm currently working on a CST paper that posits time can emerge from causality. CST. What's CST? She's not good for, no, she's not good for science communication, but she's very, very good at, causal set theory. Oh, that'd be interesting. If you're looking for a collaborator, to shoot me a message. I'd be happy to take a look. Or if you just want me to take a look, I'm happy to look at that too. Because I've wanted to think about causal set theory for a while. I just haven't been able to get into it. I didn't know that you did causal set stuff besides just string theory. So my opinion on Sabina is that Sabina Hassenfelder is that she's very, very good at explaining physics. Very, very good. She tries to go outside of physics rather frequently, and she also, like, when she's not just explaining known stuff, she is speculating a lot and being very cynical, and I don't like that at all. Why does our Earth's magnetic field have poles like a normal magnet? So the simplest kind of magnet that you can make is a dipole. There are no monopoles where the fields go out in all directions, and so the simplest and the most straightforward magnet is going to be, it's going to be a dipole magnet. And so anytime that you have charge roughly circulating, you will have a dipole magnet, and then perhaps some corrections depending on how that charge is moving. If it's, wiggling a little bit or whatever, the magnetic field shape might get a little bit more complicated. But generally, it will be a dipole plus corrections. You have to fine tune things very, very carefully so that you have a zero dipole moment that's zero, magnetic dipole moment that's zero. And so that's what a normal magnet is, and that's what the Earth is. Sabina has completely criticized the scientific infrastructure, so to speak, to a crazy degree. Sabina is extremely smart and has papers, I think, but she has gone off the deep end. Yeah, that's roughly my view. For sure, I can send you some stuff. Yeah, awesome. I'd love to. Causal set theory, causal dynamical triangulation. That's related to causal set theory, right? And strings mostly. Well, yeah, no, that sounds neat. Sorry, I should hydrate more. Don't want to get sick. I've always wondered if objects further away in space are moving away from us faster, but they're also older. How do we know that the expansion we see isn't just expansion from the past? Well, it is expansion from the past, but we can see that there's expansion at all points in the past. It's due to spin. If the Earth wouldn't spin, it would have no magnetic field. Well, that's true. It's due to spin. Okay. It's due to spin and due to the flow of essentially liquid metal in the middle of the Earth. Not literally the middle, but like the outer core, and then I think partially the mantle, but mostly the outer core, which is liquid metal. And so because you have, like, when you have spinning liquid metals, that can create magnetic fields. If you have the small seed magnetic field, that small seed magnetic field can get quite a bit larger. And from the Ogopogo, thank you for becoming a tier 1 Twitch subscriber. I appreciate that a lot. Man. My jaw be hurting. Still have this sinus infection, which is rough. The current paper is a toy model 1+1D that shows you can recreate triangulated spacetime of causal dynamical triangulation from just causally ordered data in CST. I'm surprised that hasn't been done. Not to say that it's not about it, it's a bad idea, but like, I'm surprised that hasn't been done. I thought that was like the main idea. All right, I'm gonna bring up a guest. No, never mind. We don't have any guests yet. Who let the Ogopogo out of Okanagan Lake? I don't know what that means, but it sounds like it's a joke, and I appreciate the joke. Let's bring up Ginga P. Ginga P, you are currently on. What questions you got for me?
Hello.
Howdy. What you got?
Sorry, let me turn off your stream or mute it.
Yeah, sure.
So I'm just an engineer guy. Like, I've got a bachelor, so I have some understanding of, like, like I'm aware of like the general stuff with black holes being, condensed matter or releasing Hawking radiation through like the quantum tunneling, like you were saying. I'm kind of curious for the way that black holes behave. I'm just gonna like say like this is just a like a wild theory, but in a way, are they a region of space-time that if you traveled through, let's say, the event horizon, that you would actually be not necessarily going into the physical space from an outside perspective, it's like in a locality, like, it's this big. But if you
Hmm.
travel into it, it's almost like you're traveling into the rest of the universe's future. So you're essentially basically in the black hole, it's kind of confined in its own causal boundary, which I think I asked a question earlier about the event horizon. But
Hmm.
in a way, the Hawking radiation, as you're approaching the black hole, if the time for you is slowing down, how does how do you receive that Hawking radiation as you're approaching where it's being emitted from?
You
Does it become
don't.
brighter?
So you're not going to catch all of the Hawking. Like if you were just hanging out near the event horizon of black hole, you're not going to catch all of the Hawking radiation. Um, the only way to catch all of the Hawking
Well,
radiation is to be infinitely far away from it, or arbitrarily far away from the black hole.
yeah, I
Um,
guess I don't mean all of it, but I mean like let's say because it's in the infrared, it's like the essentially it's black body like heat, right? It's
yeah, it's not in the infrared; it's deep in the radio part of the spectrum. But sure.
okay. So in that, does it become shifted as you're approaching the black hole in your time relative to like if you're outside of the black hole's gravitational influence
Hmm.
enough to where the time dilation doesn't matter to you as you get closer to it and your experience of time I guess becomes faster from an outside perspective, does that Hawking radiation
Yes.
shift
Yes.
into
So yeah, I know exactly what you're saying. So what the Hawking radiation will seem bluer to you. The Hawking radiation that you do catch will seem bluer to you than it would to an outside observer. The Hawking radiation that's emitted to a distant observer is extremely redshifted. The Hawking radiation that comes from near the boundary, from near the event horizon, is extremely redshifted, and so they're going to see it very, very deep in the waves. You will see it bluer. There is, in fact, a problem with there's something called the Trans-Planckian problem, which is how do we deal with the fact that sufficiently close to the event horizon, the Hawking radiation is blue shifted past the Planck energy. That is a problem. It's an active it's an active question that people have of like how do we make sense of this?
and the Planck energy would be the maximum amount of energy a photon of light can have.
That's not
Or-
clear, but somehow once you get to those energy scales, quantum gravity should start playing a role.
Yeah, I guess in a roundabout way, like the way that obviously I have no physics like real physics background, but the way that I almost view black holes is not that you're actually approaching a in quotes like singularity. It's almost that you're moving through a region of space that is essentially you're just continuing to move into the black hole, and you are almost like one. I guess once you get past the event horizon, you're confined within that causal there's no
There's no way
like you
out.
can't get information outside of it.
Yep.
But within that black hole, like not that you necessarily have access to the information within the black hole, but wouldn't it be like if you are like you could approach the region of space that formed that black hole? Like you'd almost be going back in time to when the black hole first formed, right? Because the black hole when it formed, the that region has so much energy that becomes time dilated in itself.
So it's
And
really
so
not
as you
clear what
approach
the
it,
inside of a black hole is like.
yeah, I mean that's
Like that's the
yeah,
reality. Like we have no idea
but
what the inside of a black hole is
and
like. In
yeah,
classical
and there's
GR, a rotating black hole or a non-rotating black hole, you can't get to you can't see the singularity until you get to the singularity, at which point you're dead. In a
mhm.
non-rotating black hole, sorry, in a rotating black hole, you could loop around the singularity a few times. You can do all sorts of things. Still can't get to the singularity, but you could, you know, loop around it. And, you know, there's even diagrams for these things. If you look up Penrose diagram for Penrose diagram, curve black hole, I can put it on the screen for everybody watching. Let me see if I can find it. This is a decent one. But the point is that singularities are the wiggly bits. If you guys can see this, the singularities are the wiggly bits. And so you could see the singularity once you're inside a rotating black hole, because it can give off light that can get to you. But you know, that's a very idealized scenario. It's really not clear what a black hole is actually like on the inside. Nobody has any idea. It's almost impossible to say at this point.
I was going to say it seems essentially impossible to, like, without theory, to probe what that is because of the boundary.
Yep.
So I guess the final question, because I don't want to take up too much of your time.
Sure.
Do you think it's obviously it's an important part of physics to explore, because it helps us understand more fundamental laws about the universe, but in a way, the theories and stuff that we are proposing for black holes, how do you think that fits in with the current, like, scientific method of, it has to be, I mean, for good science, it needs to be falsifiable or provable, and without being able to probe within black holes, where do you think that, like, there probably needs to be some way to, like,
so what you would do is you would come up with a theory of quantum gravity. You would test that theory of quantum gravity in other ways, because quantum gravity is not restricted to only inside of a black hole. In principle, if gravity is indeed quantum, then it would be quantum everywhere, and you would just have to probe you know, precisely enough to know that. And then once you've verified your theory of quantum gravity, well, then you would go apply it to black holes. You'd be like, well, we have this correct theory of quantum gravity, so it'll tell us what's going on inside a black hole.
And but without being able to probe within the black hole, do you?
But I guess look, we can't probe within the middle of the sun. But what we can do is we can understand how hydrodynamics works. We can understand how gravity works. We can understand how plasma physics works. And if you combine all of this stuff that we know about, that we can test in a lab, then you can come to conclusions about what's going on at the middle of the sun. And those are reasonable conclusions to come to, because they're based on verified physics. That's what I'm saying. So we would do the same thing with a black hole. At least that's the idea.
Fair enough.
All right, I'm gonna let you go.
Well,
thanks for the questions.
For your time.
Of course. Now, Anthony Char just joined, $5 a month. Thank you so much, Anthony Char. I do appreciate it. You now, by the way, if you didn't know, not only do you get access to asking your questions here and getting your questions answered here, almost guaranteed, because, you know, there's fewer questions if you become a member. You also get access to my debate notes. You get access to a special channel on the Discord server. You get access to special emojis and whatever app that you're using, whether it's YouTube, TikTok, or Twitch. So there's perks to becoming a supporting member, aside from just supporting a creator that you like. Is electron a wave that is spread out a little, or is it a point? So electrons can be localized at a point, but they do tend to be waves, yes. Past the event horizon, we don't have a good description of what is there. Yeah, roughly, yeah. Have we talked about how the energy within humans are very much like black holes in physical form? They're not, though. They're not like that. My understanding is that past the event horizon, your future is the singularity. That's true for non-rotating black holes. And it's true for non-rotating black holes if singularities exist, but I suspect singularities just don't exist. I have a black hole within me, so do you. I challenge you to get to the singularity of any of us. Well, look, it's generally impolite to talk about each other's black holes. Right? That's generally just not a polite thing to do. Humans, waves, and motion. Well, yeah, humans are made of particles, and all particles are waves, so sure. From the Ogopogo, it's not clear what the inside of a black hole is like. The documentary Interstellar covers this. They go into one and see what it's like. Oh, good point. Do black holes block gravitational waves? Gravitational waves can fall into them. Gravitational waves can also be bent by them, but they don't necessarily block all gravitational waves, only the gravitational waves that would fall in. Is a black hole just the imaginary numbers of physics? I don't really know what that comparison would mean. Like, black holes are real physical things that we can see in the universe. Like, they exist. I believe astronomy has a pretty low sigma requirement compared to other branches because of observation limitations. Not really, no. Probably way higher, honestly, than like anything besides physics, but particle physics in particular has a very high sigma requirement. CDT is more closely worked on in terms of LQG recently. Spin cubes have mathematically formally bridged CDT and LQG. Oh, that's neat. This is a lot of attention leaving a hole for CST CDT exploration literature. Oh, yeah, I wasn't familiar with that. I don't really follow LQG stuff that much. I kind of just steal it for cosmology. But emojis, you say? Indeed, emojis. What do humans represent energetically? I don't think they represent anything energetically. Interesting view about black holes and not talking about them. Oh, well, yeah, I mean, it's just kind of impolite, right? In why the skepticism on singularity? I've heard you say that a few times. So in the past, the most similar singularity that was considered in the past was electromagnetic singularities. So if you can get arbitrarily close to a point charge, and a point charge would have the electric force, the electrostatic force, arbitrarily close to a point charge diverges to infinity. And so that's a singularity, that's a problem, right? Except once you take electromagnetism and you quantize it, you make it a quantum field theory, that singularity just disappears. It was an illusion the whole time. And so I suspect a similar thing will happen with general relativity. Once we figure out some sort of quantum theory for general relativity, then I imagine the singularities will just disappear. Premier Property Intelligence, thank you for sharing the stream. I appreciate that. I'll message you privately and we can work on some things. Yeah, cool. I mean, like, if you want to, it's no requirement. No, it's not required at all. But, you know, if you're looking for somebody to bounce ideas off of and, you know, work on stuff with, I'm always happy to work on things that interest me. If you were 12 billion years in the future and you were looking at Earth, what energy would humans be? Humans aren't energy. Humans are just stuff. Stuff can have energy. Completely out there idea, but if gravity waves act like waves, could you theoretically create constructive interference between gravity waves and create really dense pockets of spacetime? Well, yeah, you can, but those will be temporary, right? They'll fluctuate. How does quantum field theory make this electrostatic singularity disappear? So there's this thing called charge screening, where basically as you get closer to a point charge, its charge effectively decreases. Sorry, let me make sure that I get this right. Yeah, its charge effectively decreases. Or is it increases? No, I'm sorry, its charge increases, and that charge is screened away, further away. But the point is quantum field theory just, one of the implications is that quantum field theory is that there are no point charges, right? Like electrons are waves. So like the idea of like a point charge that has some electric charge just doesn't exist. It's not a real thing. From Get Stanfield with the $5, is there any real threat of a supernova occurring within a 100 light year span within the next 100 years? Thanks. So supernovas occur in galaxies like ours about once every 100 years. So no, there's not really a real threat of that. I'll bring up another guest in a minute. I just want to get through these remaining questions. Why electrons don't fall into the nucleus, and is it possible? They don't fall into the nucleus because they're not little particles buzzing around. They're more like a cloud surrounding the nucleus, held up by the electrostatic force. This stuff would be energy in some form. No, energy is not a stuff. Energy is a property of stuff, not a stuff itself. But with standing waves, regarding the gravitational waves, standing waves, they have a peak and a trough, and a peak and a trough. So the peak would be the high density, and the trough would be the low density. So it would be temporary. It wouldn't exist for extended periods of time. Hey, I'm just a hobbyist, but I'm learning about modular flavor symmetry models, Ferruglio-style A4 constructions, the whole fermion mass and mixing, etc. Any way you can answer a specific question? I'm probably not the person for it because I don't do high energy theory. It's not like it's not my area. But I mean, you can always ask a question in the Discord server. What is the speed of electrons in electricity? The actual electrons drift like on average very slowly. I meant imaginary numbers because they are proven by adding the z-axis basically. So like black holes will become more understood if we just find the hidden axis. Sorry, I'm very you don't have to apologize for being uneducated. No, the black holes won't become more. There isn't a hidden axis, probably, unless you're a string theorist, of course. But Yeah, I would say that it's probably not a good analogy. You said people with stuff. Yeah, people are the stuff. We're like atoms and stuff. All right, let's talk to Jesse. Jesse, how's it going?
Not too bad.
Glad to hear it. What questions you got for me?
So because black holes' masses are so great, it absorbs light, right?
Well, light can fall into it and it can't get out.
So because of that, because the black hole's mass, does it live technically like at light speed in a way?
No, black holes, they can just be sitting there. They don't got to be moving.
Okay. Because I just had because when you get close to a black hole, time slows down, right? Kind of like you're moving at the speed
Time
of
slows
light.
down. Well, it's a similar phenomenon. Time slows down for you relative to other people. So in the amount of time that you'll experience, say 10 minutes, it might be 5 hours for somebody who's far away. And it's a similar phenomenon to what happens when you're traveling near the speed of light. But it doesn't mean you are traveling near the speed of light. These are just, they are two distinct phenomena that give rise to one of the same effects.
Okay. So my main question was, say a black hole could perceive, would its lifespan seem short to itself?
I have no idea what it would mean for a black hole to perceive.
Like
I don't know
say
how
like
that
say
would
like
work.
say like it's just like a hypothetical. Obviously, it's
No,
not
I know,
true.
but like the thing is, as a black hole, so stuff could fall into a black hole, and so it could see light. If like by seeing it means that like the light falls into it. How it would measure its lifetime, I don't know. You'd have to give me more than just.
But you know,
you'd
like
have to like specify it.
so like a light particle from the moment of the Big Bang, because it's moving so fast, it's pretty much it lives and then it directly hits your eye. Right? Like
Not really. There is no well-defined notion of what a light particle experiences because it's not a valid inertial reference frame. So like when we talk about what it's like to move close to the speed of light, what we're saying is that there's a mathematical formula that you can figure out what a clock would do if it were going this speed or if it were going that speed, right? And so that you can compare those two speed, like what you can compare what the clock would do when it's going this speed as opposed to when it's going that speed. The thing is there is no mathematical formula to tell you what will happen if a clock is going light speed.
I'm sorry, I didn't get that. My family walked in.
So the point is there are mathematical formulas that will tell you what a clock will do, how fast a clock will tick, if it's going, say, at 90% the speed of light or 95% the speed of light or whatever. But there is no formula that will tell you how fast a clock will tick if it's going at the speed of light. So there's just, that's what we mean when we say, like, from the perspective of something going near the speed of light, time slows down. What we mean is there is a way that you can calculate what a clock will do when it's going that fast. There is no way to do that for the speed of light. So there's no way to answer that question, what it would be like for a clock that's moving at the speed of light.
Okay. So it's kind of rhetorical.
No, it's just not a well-defined question.
Yes. Okay, well, thank you for your time.
Of course. Thanks for being here, Jesse. All right, I'm going to answer some more questions and we'll bring up another guest. You said people with stuff. Yes. Can you explain how science understands humans and physical stuff around us as simply atoms? Yeah, like atoms are the fundamental building blocks of matter. So if something is made of matter, then it's made of atoms. But they're not looked at the same as every other energy. Energy is not a thing. It's not a stuff. What if it's just not reflecting back to us because it's like a corridor of massive time? What if my grandmother was a bicycle, right? How do moving electric fields create magnetic fields with relativity if the speed of electrons is so slow and relativistic effects are noticeable when approaching C? So individual electrons. So, okay. Yeah, the point is that you don't need fast moving charges because in some sense, magnetic fields kind of take into account Like the magnetic fields kind of get a boost. What's the best way to explain this? When you're doing these calculations, there's the electric field and then the magnetic field, and the formula for the magnetic field has an extra factor of c in it. So even though things might be slow relative to it, relative to the speed of light, the magnetic fields get a boost in a sense. So you can have slow charges moving that create magnetic fields because the magnetic fields kind of get a boost relative to the speed of light. And this just pops out of the equations actually. How likely is it that the event horizon is a signature change in space and not a literal physical boundary? Well, it is a signature change in space-time. Event horizons are not literal physical boundaries. Right? They're not boundaries. What is energy to you? Energy is a number which is conserved. It's a conserved quantity associated with a particular symmetry. Is a black hole not a group of atoms held together by energy? No, a black hole almost certainly doesn't have any atoms in it. Could the universe be anisotropic? It could be. Yeah, it could absolutely be. Could the cosmological principle be wrong? Yeah, I suppose so, but we would need pretty strong evidence for that. All right, let's bring up a guest. Let's bring up Empiricist from Discord. Empiricist, you are on the show. Empiricist, how's it going?
Hey, how's it going? Yeah,
Pretty well.
so I had a philosophy of science question, not
Sure.
necessarily like physics. Okay, so in Erica's uh lectures on evolution with Will Duffy,
Mm-hmm.
part of the start was saying that like science can't explain the supernatural. Like if there is a supernatural phenomenon, science can't explain it or study it. I was just wondering, I mean, I don't know if you accept that that definition, I guess, but I was just wondering how supernatural is like defined such that that's not just a tautology.
So my view is that if any good definition of supernatural will make that statement a tautology.
Okay, yeah, because like, I mean, I feel like, I mean, there are things that people say are supernatural. Like, I mean, souls are probably the easiest one. So,
Mm-hmm.
like, if I mean, people agree on that, but if souls can, yeah, verifiably exist, then like it would just
Wouldn't they just be natural
like
again?
yes,
Yeah.
yes, like anything
Yeah.
science yeah could explain, like it would just be natural. Like in the same way that like I mean, if you didn't understand quantum physics, then like quantum physics is supernatural compared to chemistry.
Yeah, so generally the definition that I would offer for supernatural would be something like something that in principle cannot be explained using the natural sciences.
Right, but then like are ethics supernatural? Because that like is mathematics supernatural? It's just
Or I should
I'm
say
just
cannot
not
be
sure.
accounted for, perhaps.
Okay.
Of course, we're talking about phenomena, like real phenomena. We're not talking about like concepts. And so like I would say that that's like a category error to say that like ethics are supernatural, because ethics are like conceptual rather than like a real thing. The idea behind a soul being that this is like a real thing. It's just like not physical in nature, but it's like it has some sort of ontology to it. And you know, whereas I would say that like the number 5 doesn't.
Okay. Yeah, all right. That's pretty much my question.
Okay.
Yeah, I was just kind of like she said that and I thought it was just kind of weird because she didn't elaborate on it. Erica
Sure.
Gibbon, by the way.
No, I know.
And yeah, it seemed kind of like non-confrontationalist rather than like an actual useful way of defining science.
Yeah, I mean, look, I haven't seen any of those, so I can't comment on it. But yeah, that's. I mean, I gave you how I would define these things.
Yeah. All right. Yeah. Thanks.
Take care. All right, let's answer some more questions, and we'll bring up another guest. Is it certain black holes? Wait, hold on. I need to scroll back a little bit. If E equals mc squared, then energy is equivalent to mass and can be converted as such. Yeah. So mass and energy. So you can think of mass as like one kind of energy. But it's still just a number. It's not like a thing in itself. Is it certain black holes do not have atoms within them? Yeah. I mean, atoms can't survive the extreme gravitational stresses that would be required, or that would be present within a black hole. Where do the photons go, though? They go inside the black hole. My reason is simply because there's so much electrons there, which makes it noticeable. Effects are 10 to the minus 15 different or so, but the electron count is 10 to the 16 or so. Yeah. So there's that too. But there is a relative factor of C between the electric field and the magnetic field, right? Like there's a relative multiplicative factor of C between those two. So that plays a role. Like you'll see E over C, or like C times B. That kind of thing. As a layman, I just go off the reflection of the image of M87 galaxy. I don't understand. Dark matter is still on that variance thing you said, but black holes are very real, Anthony. They are. How much do you think the advancement of the standard model is gated by neutrino mass measurements? How many leads would close open if we had a solid specific number for their masses? I don't know if any would open or close if we had specific numbers, unless those numbers were like very, very special. But if we had an explanation for those numbers, that'd be really good. What happens with the strong force of black hole densities? Well, we don't know. Black holes don't have to be dense. Black holes can be very, very sparse, if you will. But we don't know exactly what happens at singularities, if such things exist. But like, yeah, I mean, at some scale, these forces probably break down to like more fundamental, or they probably join or break down to more fundamental things, whatever it might be. But QCD will still operate deep within a supermassive black hole, no problem. Based on what we can observe, is the age of the universe young, older, middle-aged, relatively? It depends on how long the universe will last. Which we don't know. Have you tried using GPT 5.5 Pro to help with your research? I haven't. I don't have Pro because Pro's expensive. All right, let's bring up a guest. Let's bring up Unseen Gleam. Unseen Gleam, how's it going?
You hear me?
Yeah, I can hear you. It seems like there might be some confusion here, so hopefully I can clear something up.
I wouldn't call it confusion. I would just say that, and again, like I'm not trained in scientific background. The main person I talk to is my uncle, who is very learned in the subject. But my understanding is that everything around us is energy that is vibrating in some form. Is that?
Yeah, it's not really a correct description of like the way that we think about physics these days.
How would you describe the tree that I see outside, or the leaf? What is actually happening in the like physics description, like that brings that image into my eye? Because like we know that I'm not actually seeing what's there. So
well,
like what is happening? What is happening that's making a difference between the green tree, the green leaves, and the brown bark?
Yeah, sure. So look, so the tree is made of stuff. It's made of atoms, right? I hope we can agree on that. Those atoms behave differently when they interact with electromagnetic radiation, light. So the green leaves, the atoms are arranged in such a way that the light it absorbs red and absorbs reddish light, it absorbs bluish light, but it reflects greenish light. And so when the light from the sun hits the greenish light or hits the leaf, the green light will be reflected back to your eyeballs, and that green light makes its way from the leaf to your eye, and you see green. The same is true for the brown bark, but the brown bark's a little bit more complicated, and so the light that gets back to you is sort of like a muddled mixture of kind of the primary colors, blue, green, and red, and you end up with something that looks like brown. So what's happening is you have atomic configurations that are arranged in certain ways. Because they're arranged in those ways, they interact with light differently. And then the light carries that information back and forth between you and the tree.
So I'm perceiving, I guess I'm trying to understand what exactly my eyeballs are perceiving.
They're perceiving light.
Okay, perceiving the light of some source in the distance, right?
Well, I mean, it depends on how far away the tree is, I guess, right? But yeah, the light bounces off of something, or maybe it's emitted by a light bulb or whatever it is. The light, wherever the light comes from, it comes from somewhere else, and then it goes into your eyeball. That light then is absorbed by certain chemicals in your eye, and that triggers a biological response, which then sends it to your brain, and so on and so forth.
So if I go outside into a very dark place and I look at a star that was created, I'm seeing something from I don't know the age of the universe, tens of
Well,
billion, whatever.
The
How many
stars that
billions
you can, the stars that you can see are going to be at most a few hundred light years away. Maybe 1,000 if you're lucky, if you have good eyes.
We can use any. I've seen the
Yeah.
Andromeda Galaxy through binoculars.
Yeah, there you go. So that's 2 million light years away.
Whatever that. So if I'm looking at that, what is less real about that experience versus the thing that's right in front of me?
It's not less
Like
real.
Okay, so like, so what am I seeing that you're saying it's just as real, right?
It's just the thing you're seeing happened a long time ago.
Okay. I guess in my experience, at least, you know, and I come from an extremely unique point of view, but in my experience, when you look at these individual places in the galaxy and your mind comprehends them as something different than something that's right there at that moment in time, because when you're younger and you look up, you usually don't know these things, and you're like, you perceive a star in the sky as like that's happening right now.
I'm sorry to cut you off. I just realized I missed an appointment that I have to
Okay.
take.
I really appreciate you
I appreciate it. I thought my appointment was at 1, not at 11.
Yeah.
So everybody,
No,
I'm
it's
going to cut off the live immediately. Sorry. I apologize to everybody who's been waiting and has good questions, but yeah, I need to go take that. Take care, everybody.